Two more examples following up on the previous video. Find the tangent plane in a normal line for z is equal to x cosine y minus y e to the x at the point 0, 0, 0. How do we do this? Okay, so tangent plane, well, we should be able to do by now f of xy is equal to x cosine y minus y e to the x. We know we need partial derivatives here. The x partial derivative is going to be cosine y minus y e to the x. The y partial derivative will be negative x sine y minus e to the x. And we need to evaluate all three of these at 0, 0, 0. X and y are 0, 0. Z is then just comes as long as 0 for free. F of 0, 0 is 0. The x partial derivative of f at 0, 0 going to be cosine 0 is 1 minus 0 times e to the 0. That's 1. The y partial derivative of f at 0, 0 is negative 0 times sine 0 minus e to the 0. That comes out as negative 1. Okay, so we have all our information necessary for the tangent plane. So this is going to be z is equal to, using this from the last slide here, f of AB, f of 0, 0 is 0, plus the x partial derivative. The x partial derivative here is 1 times x minus 0, plus the y partial derivative is negative 1. And we're doing this times y minus b here is 0. Z is equal to 0 plus 1 times x minus 1 times y. Normal line here, I just kind of snuck this in without talking too much about this. Let's realize here, how do we come up with equation of a normal line? Well, for that we should be thinking about the normal vector. The normal vector here is just going to be, in general, minus the x partial derivative minus the y partial derivative and 1. So in this case, that would be negative 1. Negative of negative 1 would be positive 1. And then 1 here. So this would be our normal vector here. How do we write down parametric equations for our line? That mark is dead. Okay, line. So x is going to be x naught is 0 plus t times negative 1. Y is going to be y naught is 0 plus t times 1. Z is going to equal z naught is 0 plus t times 1. So we can just very succinctly write this as x is equal to negative t, y is equal to t, z is equal to t. Okay, so that's one example to do. A second example here, find points on the graph of z is equal to 3x squared minus 4y squared, at which the normal vector 3, 2, 2 is normal to the tangent plane. Okay, so what do we realize here? Well, once again, our normal vector here is going to be negative the x partial derivative at AB, negative the y partial derivative at AB, comma, so I shouldn't write n is equal to this, comma 1, I want n to be some scalar multiple of this. If two vectors are scalar multiple of each other, let's say non-zero, to throw a non-zero there, get rid of degenerate conditions here, these two will be parallel to each other. They both be normal to the tangent plane. Okay, so what are we asking for here? How do we make this a multiple of this? We better get lambda. Lambda has to equal 2 or negative 2, depending on what the signs here are. Okay, before we do anything else, let's go ahead and get the partial derivatives plopped in here. The x partial derivative, we'll call this f of xy. The x partial derivative is 6x. The y partial derivative is going to be negative 8y. So now our vector here is going to be negative 6x, comma, negative 8y is positive 8y, comma 1, and we want this to equal 3, 2, 2. Now there's only one choice for lambda here. We need to multiply, the 1 slot here. The z slot is 1. We need to multiply that by 2 to get 2 over here. So negative 12x, comma 16y, comma 2 is equal to 3, 2, 2. And to finish off this problem, we just need to solve the equation. Solve the equations that negative 12x is equal to 3, or x is equal to negative 1/4, and 16y is equal to 2, so y is equal to 1/8. Okay, so this is, we have the x coordinate of our point, we have the y coordinate of our point. X is negative 1/4, y is 1/8, and then the z1 is going to be 3 times negative 1/4 squared minus 4 times 1/8 squared, whatever that simplifies down to. This will be the point that was requested.